In this lecture here, we now want to start talking about polynomial functions and their graphs. So this is what we've done. So previously, we've talked about quadratic functions. And so, quadratic function is a polynomial function. So just something like this, right? So f of x is equal to a times x minus h squared plus k. And what we saw was the graph of this quadratic function was a parabola with a vertex, not center, vertex hk. Okay, the turning point was vertex hk. And so we talked about all the properties of this and how you graph it. So in this section now, what we want to do, we want to expand on this for polynomial functions in general. So stuff like this. What does the graph of this function look like? Something like 2x cubed minus 3x plus 7. I don't know. Or even something like this. This will be actually the last problem we do. Something that looks like this. X cubed times x plus 2 squared times x plus 1. So there's a lot going on in that last one here. So what we're going to do over not just a single lecture, I'm going to break this one up into multiple lectures. I'm going to talk about all the different properties of these type of functions, and then we're going to build towards how you sketch their graphs. All right, so here's what we're going to work on. First thing we're going to do is we're going to identify polynomial functions. We're going to recognize characteristics of graphs of polynomial functions, and we're going to determine end behavior. This is really important. Determine the end behavior of a function. So these first three things is going to be lecture number 1. So this video lecture here. Then I'm going to follow it up with a lecture talking about using factoring to find zeros of polynomial functions, and then identify zeros in what's called their multiplicities. So this is going to be lecture number 2. And then that's all going to build towards these final 2 bullets here. So how you understand the relationship between the degree of a polynomial function. Okay, so I'll remind you what a degree is in a little bit, and the turning points. And then finally, what we'll spend a lot of time on is how you graph polynomial functions. So this will be lecture number 3. And I'm also going to pull out the graphing calculator for a little bit here, so you can see how to use the graphing calculator for a lot of this. All right, so let's jump right into this first lecture here. Okay, so what exactly does a polynomial function look like? So let's let n be a non-negative integer. Okay, so n is going to be something like this. Okay, and let a sub 1 comma a sub n minus 1 comma all the way to a sub 2, a1, a0 be real numbers with a sub n is not equal to 0. So this function defined by the following, and it looks a lot harder than it is. F of x is equal to a to the n to the x to the n plus a to the n minus 1 to the x to the n minus 1 plus all the way to a to the n a squared x squared plus a1x plus a0. Let me just show you what this might look like, okay, just so you see here. So this might be 5x to the 7th power plus, I don't know, 3x to the 6th power minus, and then what's going to happen is you could even have something like minus 1/2 x to the 5th, and this would just keep going down until you got to something like this. I don't know, 2x squared minus 12x plus 3. Okay, and some of these terms might be missing. Like you might not always have 7, 6, 5. It could even be something as simple as this. F of x is equal to 1/2 x to the 12th power minus 2. Like it doesn't need anything in between here. But what's going on here, this is called a polynomial function of degree n, right? So this one here is degree 7. This is degree 12. What's really important is this a sub n here. Okay, this first coefficient for the highest degree variable here. Okay, so the coefficient of the variable to the highest power, so the highest power here is called the leading coefficient. Okay, and the leading coefficient is very important. Okay, so when you look at something like this, f of x is equal to 3x to the 7th power plus 8x minus 12. What we see here is this is a degree 7 polynomial, and its leading coefficient is the number 3. So if you look at something like this, f of x is equal to minus x to the 4th power plus 2x minus 3. You see here the 4, this is a degree 4 polynomial. And the leading coefficient, see how there's a negative here? The leading coefficient is a negative 1. All right, so this is just how you define it. So it's a lot of, writing here to define something that's pretty straightforward. What you need to really key concept here is what is the degree of this polynomial, and then finally what is the leading coefficient. Okay, so what we're building towards, all right, is what the graphs of polynomial functions look like. So polynomial functions are what we call smooth and continuous. So polynomial functions of degree 2 or higher have graphs that are smooth, so you draw smooth curves, okay, and the graphs are continuous. So by smooth, what we mean is the graph contains only rounded curves and no sharp corners. So when we're going to sketch the graph of a polynomial, it might look something like this, okay? Notice how I sketch it. Smooth curves. Something like that, okay? So smooth curves. Okay, just smooth. You're gonna nice and clean here. All right, by continuous we mean that the graph has no breaks and can be drawn without lifting your pencil from the rectangular coordinate system. So like when I graphed this smooth curve here, all right, I didn't take my pen, in this case my stylus, off the screen here. All right, so what this means, just also when it, continuous here, just kind of a side note. The domain of all polynomial functions is from negative infinity to infinity. That's not always the case for the range, okay? But for the domain, it's all real numbers, okay? All right, one of the most important things about graphing polynomial functions is understanding the end behavior of a polynomial function. So when I refer to the end behavior, let me go back to this graph. It's not what's going on in the middle here where there's all these turns. The end behavior is, notice how this arrow here is indicating that it's going up and up and up and up forever. That's the end behavior to the right. So as x increases without bound, okay, it looks like the graph is going up to positive infinity. And the end behavior here as x decreases without bound, becomes more and more negative. Looks like it's going down to negative infinity. Okay, so the behavior of a graph of a function to the far left or far right, so as x decreases without bound, or as x increases without bound, is called its end behavior. So although the graph of a polynomial function may have intervals where it increases or decreases, like you see here, increasing, then decreasing, and then increasing, okay, the graph will eventually rise or fall without bound. What that means, as I said here, is these arrows going up to infinity or down to negative infinity as it moves far to the left or far to the right. So the way you determine this, okay, this is really important right here. The sign of the leading coefficient, so going back like this 5, this 3, this -1, the leading coefficient and the degree of the function reveal its end behavior. So looking at the degree and leading coefficient, all right, reveal end behavior. And this is one of the first important concepts that you'll see later on in our lectures. One of the most first and important concepts, all right, for figuring out what the graph of a polynomial function is going to look like. All right, so here's the deal. As x increases or decreases without bound, this graph eventually rises or falls, okay? All right, so you're either going to have arrows that are going up at one end or falling, going down like this, okay? So it could also be going up this way. It can also be falling this way. And this chart right here is really important for figuring out what this graph is, what the end behavior of graphs are going to look like. Okay, so just so we note here, n, note the number n here. N is the degree of the polynomial. Okay, so if the degree is odd, okay, so a number like, 3, 5, 7, 9, 11, so on. Okay, even the number 1 here. Okay. If the leading coefficient is positive, the graph falls to the left and then rises to the right. So what that means is when, however we're going to sketch the graph, I know as x becomes more and more negative, the graph is going to fall. Okay, and as x becomes more and more positive, increases without bound, the graph is going to shoot up. Okay, I don't know what's going to happen in the middle, and that's what we're going to spend a lot of time on in the coming lectures. But I know that the end behavior, it's going to decrease without bound as x decreases, and it's going to increase without bound as x increases. Now, if the leading coefficient is negative, okay, the graph rises to the left like this, and it falls to the right. So we don't know what happens in the middle, how many times it's going to turn, and we're going to talk about that. Okay, but I know the end behavior. Okay. So now if n is even, so the degree is 2, 4, 6, 8, 10, whatever, an even number. If the leading coefficient is positive, the graph rises to the left and rises to the right, okay, as x increases or decreases without bound, okay? It's going to be this somewhat parabolic shape, right? But we don't know what's going to happen in the middle here. Now, if the leading coefficient is negative, okay, the graph falls to the left and falls to the right. Okay, it's going to be that like inverted parabola, the upside down parabola. Okay, so let's put this to work so you can kind of see how this leading coefficient works, all right? So I have this first one worked out. So let's use the leading coefficient test to determine the end behavior of the graph. And if you were to plug this into your graphing calculator, right, let me even do that for you right here. Okay. Let's take, so to graph something in your graphing calculator, right? Let me just minimize this. You're going to go y equals, you're going to get x to the 4th minus 4x squared. And this is what the graph looks like. And you can see I have it replicated right here. Okay? But without looking at the graph, okay, determine the end behavior of the graph of this function. Okay. So the first thing you're going to do, you're going to look at the degree. Okay, so it's an even number. Okay, so looking back here, all right, even number, right here. So it's either going to increase without bound, all right, as you go to the left or to the right, or it's going to decrease without bound as you go to the left to the right. So it can only be one of these two options. So the next thing you need to look at is the leading coefficient. In this case, there's, a 1 here. So what this means is, okay, the leading coefficient is positive. So the graph rises to the left and rises to the right. And look, you see that. As you go to the left, the graph is eventually going to shoot up. And as you go to the right, the graph is going to eventually shoot up. All right, so the degree of this function is 4, which is even. Even degree functions have graphs with the same behavior at each end. And here the leading coefficient is 1. It's positive. So the graph rises to the left and to the right. So what we don't know, all right, what's a little confusing here is like what happens in the middle. Okay, so what we're going to, as I've said this before, but we're going to talk about how you know that this is what happens in the middle, all right, in the coming lectures. Okay, but at least we know the end behavior of the graph. All right, let's end with this example here, okay? So we'll use the leading coefficient test to determine the end behavior of the polynomial functions, all right? These are my polynomial functions right here. Then match the polynomial function with its graph. Okay, so let's start with this. We'll go 1, 2, 3, and 4. So here's the first function. f of x is equal to negative x to the 4 plus x squared. Okay, well look here. It is degree 4, and the leading coefficient is negative 1. It's less than 0. So look, let's go back. Degree 4, okay, so it's even, and the leading coefficient is negative. So this graph was going to have to fall to the left and fall to the right. So looking forward, looking back, do we see any graph that falls to the left and falls to the right? Yes, absolutely. Here, so it's graph B. Now let's look at this one. All right, if you were to FOIL this out, okay, if you were to FOIL this out, you would actually get x squared minus 6x plus 9. But you can see it's a degree 2, but there's a cheat way to do this. You can just say x, and then there's a squared, so it's a squared, so it's degree 2. So look, again, degree 2, leading coefficient is greater than 0. So look, going back. Leading coefficient is greater than 0, degree 2. It has to rise to the left and rise to the right. So this graph here looks like this. Rises to the right, or rises to the left, rises to the right. This function here, its corresponding graph is graph A. Let's look at this one. X cubed minus 4x squared. Well, it's a degree 3, and the leading coefficient is 1, so it's greater than 0. So odd, degree 3, leading coefficient greater than 0, so it has to fall to the left and rise to the right. Well, look at this. Falls to the left, rises to the right. So this looks like graph C. Excuse me. And finally, I know we can just use process of elimination, but let's actually work through it here. F of x is equal to minus x cubed minus x squared plus 5x minus 3. Well, you can see this is degree 3, and the leading coefficient is less than 0. So odd, degree 3, leading coefficient less than 0. It needs to rise to the left and fall to the right. Well, look here. This rises to the left, and as you go to the right, it falls. So this one is graph D. Okay, so this will end our first lecture. As I said, coming back, what I'll do is I'll follow up this next lecture with here, okay? Using factoring to find what we call the zeros of polynomial functions, and then identify zeros and their multiplicities.